Welcome back. We have text problem 21-17 for lesson 29 today. As always, please get out a scratch piece of paper or a blank printout of the problem so we can work together in what I have found online as collaborative learning. So let's get into our first step, our read step. And because we're in a new block, we're starting out on some pretty rudimentary topics. They will get more complex as we get into the block. But from this problem, I see that we have some point charges, and we're looking at calculating some net electrostatic force of particle 2 on particle 1 and particle 2 and particle 3 on particle 1. So we've got point charges and electrostatic force. Next we have our draw step. It's pretty well lined out for us. For part B, in figure B, we have three particles that are in an equilateral triangle formation. So this distance right here still applies from figure A. So that's a distance D as well. Alright, as we get into our givens, we have charge 1, which is equal to charge 2, which is equal to charge 3, which is equal to 20 microcoulombs. So you're going to be seeing a lot of scaling prefixes in this block. Let me just do a quick review of some of those scaling prefixes. So, working with any standard metric SI unit, we can break it down from its base SI unit going down in scale. The first major scale times 10 to the negative 3 is milli. Then we go to micro times 10 to the negative 6, nano times 10 to the negative 9, pico times 10 to the negative 12, and femto times 10 to the negative 15. You will see all of these this block. It would behoove you to memorize these, because all we will give you is this little Greek letter in front and expect you to know it. So write these down, lock them away in your memory so that you will be prepared for any type of SI unit coming at you. Alright, let's move on to our next step. Assumptions. We really don't have any to make at this point. Next we have our tasks. For part A, we need to calculate the force on particle 1 because of particle 2. I think I've said it a million times, but use your subscripts. They tell a story, and the way I like to form my subscripts using the electrostatic force is you have the particle in question, particle 1, the force on particle 1, due to particle 2. That's the exact same way it reads in the problem. What is the magnitude of the electrostatic force on particle 1 due to particle 2? And then as we get into part B, calculate the net force on particle 1. That means we need to calculate F sub 1, 2, or the electrostatic force on particle 1 due to particle 2, and the electrostatic force on particle 1 due to particle 3. We need to do both. Those are the only two that matter. We don't have to worry about the electrostatic force on 3 due to 2 or on 2 due to 3. We're only looking at particle 1. Okay, alright, time for our physics step. It's the time of the video where you pause the video, write down the equations you think you will need for this problem, and resume, come back, and see how you did. Alright, so how'd you do? Well, our first equation is going to be the equation for the electrostatic force, which is Coulomb's constant times charge 1 times charge 2 over the distance between the charges squared times our unit vector. Now it's not I hat, j hat, or k hat, it's r hat. If we remember from our uniform circular motion, r hat denoted the radial direction, always pointing inward. In this case, our r hat represents the direction from particle 2 to particle 1. Wherever those particles may be, they may have components of I hat, j hat, k hat, it doesn't matter. It's always pointing from one particle to the other. So that's important to remember. It still represents a direction, but it's not fixed in space like our standard unit vectors, I hat, j hat, and k hat. Alright, our next equation there, it's not on our PRC, it's just the idea that our net force is going to be the sum of the forces acting on particle 1. So the force on particle 1 due to particle 2 plus the force on particle 1 due to particle 3. Okay, alright, I think we're ready to solve. So for part A, we have the electrostatic force on particle 1 due to particle 2 is equal to Coulomb's constant times charge 1 times charge 2, and in this case, looking at our drawing in part A, they are a distance d apart. So I'll put d squared, and our task is to calculate the magnitude of the electrostatic force, so I can drop my unit vector that we have listed up in our physics step. Now I can input all of my given values, and I'm actually going to write these out so you can see them. Okay, so I have Coulomb's constant, which is on the back of your PRC. It is 8.988 times 10 to the 9th Newton meter squared per Coulomb squared. Now that looks like some pretty funky units, but as we see the rest of our terms flow into our equation, we'll see that they cancel out to get us the appropriate units for our objective quantity. So I have Q1 times Q2. Well, since both of my charges are equal to each other, I can just take one of the values and square it. We do measure charge in terms of coulombs, and our distance between particle 1 and particle 2 is 1.5 meters. And our answer is 1.60 newtons. We had 3 sig figs for our charge and 3 sig figs for our distance. We have 4 sig figs here, but it's the lowest number that counts. Alright, so I'm going to go to the next slide and discuss the nature of charge, because it can be a positive charge or a negative charge, and how that affects the electrostatic force. So in part A, we have a positive charge as particle 1 and a positive charge as particle 2. Now you may know from middle school, high school, just life in general, that like charges repel each other. So if we draw a free body diagram of particle 1, the only force, I shouldn't say the only force, but the dominant force acting on particle 1 is the electrostatic force. I want you to notice the fact that the force itself acting on particle 1 is in the positive y direction. What would happen if particle 2 were actually negative? Well, opposite charges attract. So we could see the force on particle 1 due to particle 2 pointing downwards. The same could be said if particle 1 were negative and particle 2 were positive. So the sign of the charges decides the direction of the force. Okay, now you may be thinking, well, that's easy. I'll just put that into the equation. Be very, very careful. First, you need to do an analysis of the charges you have at play, do a free body diagram, and see which direction the force is pointing, such that when you put your charges into the equation, you're putting the absolute value of the charge quantity. So if one of my charges were negative, I wouldn't put in negative 20 coulombs, microcoulombs. I would put in 20 microcoulombs. I would allow the comparison of my two charges at play to decide the direction of the force. Okay. We won't get a chance to look at that for part A or part B, but you will see it in the coming lessons, and I'll make sure to highlight it when one of those suggested problems comes up. Okay, so let's get on to part B. Again, we need to calculate the net force on particle 1, which is equal to the force on particle 1 due to particle 2, and the force on particle 1 due to particle 3. Now this is well and good, but our task is to calculate the magnitude of the net electrostatic force. Well, we can't just add our magnitudes because we have vector quantities here. So if we have vectors, what should we do with our vectors? We should break them into x and y components. So I want you, using a disciplined use of subscripts, to write out the x component and the y component of the net force on particle 1. Alright, how did you do? Well, if you got it, great work. If you didn't, keep working on it, you'll get it. So what we have here is the net force on particle 1 in the x direction. And the net force is because of the electrostatic force on particle 1 due to particle 2 and particle 3. So we have both of those laid out in the x direction. And then we have the y direction, very similar, just replace the x's with y's. Well, we can save ourselves some time by drawing a quick free body diagram and see which one of these components is unnecessary. Not the x and the y, but our contributing components here. Okay, so let's draw our free body diagram. Pause the video, draw it up. Remember, we're looking at particle 1, so that is our body to isolate. Go ahead and draw the forces acting on it. Assume that the force due to gravity is not a big player in this, so you can neglect it. Alright, so here's our free body diagram. We have the electrostatic force on particle 1 due to particle 2 going directly up, and we have the electrostatic force on particle 1 due to particle 3 going off at an angle theta. Well, this is an equilateral triangle, so our angle here, here, and here are all 60 degrees. But what I've done here is essentially I have bisected this angle right here, so our angle theta is going to be 30 degrees. And we'll need that to continue on our calculation of the net force on particle 1 in the x and y direction. So let's get started in the x direction. I have the basic magnitude of the electrostatic force on particle 1 due to particle 3, but I don't have the x component. So here is my angle theta, and I need this adjacent component. So remembering SOHCAHTOA, the trig term I'll use to get the adjacent side is going to be cosine of theta. Okay? And when I go and do the y component, I have the electrostatic force on particle 1 due to particle 2 in its entirety because it is in the y direction only. And then I have the vertical component of the electrostatic force on particle 1 due to particle 3. And because I'm looking at the vertical component compared to this angle, I'm going to use my sine trig function. Now our task is to calculate the magnitude of the net electrostatic force. So if we're looking at the magnitude, then we need to square our x and y components, then add them together, and take the square root of that sum to get our net electrostatic force on particle 1. Alright, so here's our answer. We have what is more commonly referred to as the Pythagorean theorem. Moving my stuff around. We have our hypotenuse here, and we have the x and y component, or the adjacent and opposite sides. As we put those in, we know that the electrostatic force on particle 1 due to particle 2 is 1.6 newtons. Well, because particle 2 and particle 3 are identical, we can use that same magnitude and break it into our components for the electrostatic force on particle 1 due to particle 3. That's what I've done here. For the x component, I have 1.60 newtons times the cosine of 30 degrees. And then here, since they both share the 1.6 newtons, here is my electrostatic force on particle 1 due to particle 2, and this is the share of the electrostatic force on particle 1 due to particle 3. I square both those terms, add them together, take the square root, and the result is 2.77 newtons. So if you knew the mass of our point charge here, then you could calculate the acceleration of that particle as it goes off into space because of particle 2 and particle 3. Alright, that's all I've got. I will see you in class, and hope to really enjoy this block of instruction.